Hello, this is Dave from Dimensional Consulting. Today we are going to talk about datums, datum feature simulators, and simulated datums. The drawing has datum feature symbols indicating that the bottom surface of the part is datum feature A and the left side is datum feature B. The datum features are the imperfect physical surfaces of the part. To make a measurement, we place the datum features against a piece of equipment called a datum feature simulator. The datum feature simulator is physical and imperfect. Although the surfaces of the datum feature simulator are imperfect, they are close enough to be imperfect that we treat them as being perfect. We call these almost perfect surfaces the simulated datums. Datum feature A will contact simulated datum A on at least 3 points. Datum feature B will contact simulated datum B on at least 2 points. To measure the profile tolerance, while the part is first making maximum contact with simulated datum A and then contacting simulated datum B, we start at simulated datum B and go to the right exactly 30 to establish the true profile. Centered on the true profile is the one wide profile tolerance zone. In this process, datums A and B are not involved. In the theoretical world, exactly the same size and shape as the datum feature simulator is the true geometric counterpart. It is perfect and theoretical. Therefore, it doesn't really exist, but it is very important. The surfaces of the true geometric counterpart are datum A and datum B. Datums A and B do not really exist either. They are perfect, theoretical planes. Perpendicular to datums A and B is one more plane. Together, they establish the datum reference frame. A datum reference frame is 3 mutually perpendicular planes. In this example, datums A and B are the only 2 of those 3 mutually perpendicular planes that are used. The datum reference frame provides an origin and direction for the basic dimensions that locate the tolerance zone. Here, the origin and direction for the basic dimension of 30 is at datum plane B, as it and the other 2 mutually perpendicular planes establish the datum reference frame. Understanding what these terms are and how they relate to each other is fundamental to understanding how parts are dimensioned and measured. We start with what we see on a drawing. The drawing references a physical part. When we get to the measurement world, we talk in terms of what happens in the physical world and what happens in a theoretical world. On the drawing, we specify feature control frames. They exist only on the drawing. The feature control frames specify datum features. Datum features exist on the physical part. Datum features constrain the translations and rotations of the part. When we move into the measurement world, first consider what happens in the physical world. The physical part is placed on a physical gauge. The gauge is called a datum feature simulator. Datums derived from datum feature simulators are called simulated datums. These might be physical surfaces on the gauge that get touched by a CMM probe, or they might be axes or center planes that are derived from pins or holes or slots that are part of the gauge. Now step into the theoretical world. The true geometric counterpart is the same size and shape as the datum feature simulator. The only difference is that the datum feature simulator is real and the true geometric counterpart is theoretical. From the true geometric counterpart, we derive datums. They are points, lines, planes, or combinations thereof. They are theoretical. Datums are used to establish datum reference frames. A datum reference frame is 3 mutually perpendicular planes. The datum reference frame establishes directions and origins for basic dimensions. The basic dimensions are then used to locate tolerance zones. That's today's video. If you want to see more tips like this, please subscribe and visit my website at dimensionalconsulting.com.